first thing I just want to mention to you guys really quick, and sorry that the text is so small here, but under the model control window, I've just loaded up the final hydrodynamic model that you all have been working on building. So here under the model grid dropdown, I just want to show you just so that you get an idea of how easy it is to go from a two-dimensional model to a three-dimensional model. So really all that we need to do here is we right-click on layers here under model grid, and then we can just change the number of layers here in the text box. And once we save this model out, so I'm just using the standard Sigma approach. There's a few different options for how vertical layers can be integrated into the model. This is kind of the standard EFDC approach. So I just set up a 5-layer model here. And once I save this model out, it's going to be a 3-dimensional model. So there are a few things that, and the reason why I'm bringing this up now is because, a few of the considerations that you may want to make when you're thinking of, well, can I get away with a 2D model, or do I need to go to a full 3D model? One of the things that you might want to look at is my water body stratified? Are the temperatures warmer near the surface than they are at the bottom? Then that might be a situation where you think, okay, I need to probably look at doing a 3-dimensional model here. Similarly, with things like sediment transport, there may be a vertical gradient of something through your water column. And then those are the kind of situations where you may want to think about putting in a 2- or 3-dimensional model. In general, Lake T, which is the example that we've been looking at here so far, is a very well-mixed system. It's a relatively shallow lake. So there's really not any reason, at least at this stage, to go to a 3-dimensional model. But I just wanted to show you how quick and easy it is to set that up. So again, with the last lecture, I'm going to go through a quick discussion of the conceptual framework for this module. This is the temperature and dye module. Brief discussion of theory, and then discussion of the user interface and the different dialogues that you're going to be working in. And then we'll just have a few brief slides on the setup of the dye theory, and then the setup of the dye module. So again here, just for your reference, the theory guide and the user's guide. This one's for dye, and then this one's for temperature. So the conceptual framework. Now, it might be kind of hard for you to see. This text is kind of white on a relatively light color, but I'll just walk through the terms here. So as with the hydrodynamics module, we have external sources and sinks. Here, the temperature would be associated with an inflow or an outflow, and that would affect the cells where those boundary conditions are being applied and the cells nearby them. So over here on the left side of this diagram, we have the processes that are going on in the model. So all of the interactions that are occurring at the surface are modeled separately. So here we have shortwave radiation coming into the water column. That gets distributed out vertically in the water column based on Beer's law. So the temperature in the water column due to shortwave radiation is a function of depth. And the attenuation of the water, the attenuation properties of that water. So if the water is more turbid, more heat will be absorbed near the surface. If it's more transparent, heat will be able to penetrate to a greater depth due to shortwave radiation. Long-wave radiation, so as many of you probably know, in terms of long-wave radiation, water's essentially opaque. So those terms are only acting at the very surface of the water body. And here we just have our two turbulent heat flux terms, the conductive heat exchange, or the sensible heat exchange as it's sometimes referred, and then the latent or evaporative heat exchange here. So it's important here to mention as well that the user has quite a bit of control as to how these terms get applied. One interesting thing that I want to clarify is that in terms of the mass balance of the model, we can set up a model where mass loss isn't going to be explicitly included from evaporation, but in that case we would include the heat flux due to evaporation. So even though there's energy being exchanged across the air-water interface, we can tell the model, don't deduct that mass from the model domain. Leave that mass in there and just ignore that term in the mass balance. So we also have the ice module, which is integrated into the temperature module. And so that would look at fluxes between the ice itself and the atmosphere, and then also between the water body, the liquid water underlying the ice, and the ice itself. So heat exchange is happening on both sides of the ice. All of these heat fluxes are augmented by turbulence in the water column, and potentially heat exchange from the bed here. A lot of many lakes like with geothermal beds might be adding a lot of heat into the bottom of the lake, which may affect the stratification, which is what we see here on the right for the water column structure. So the near surface water layer is described as called the epilimnion. Think of these in terms of how we describe the layers of our skin. So the epidermis is the very surface layer of skin, and then we move down into the thermocline area, or the metalimnion as it's sometimes called, and then the hypolimnion, the deepest, coolest part of the lake. This is the deepest part of the lake. So we parameterize wind. Now, wind is mostly going to affect the turbulent heat exchange terms here, the latent and sensible heat exchange. And then we also have all the atmospheric parameters of the model. So the air temperature, the atmospheric pressure, relative humidity, and cloud cover. So these three terms here combine. They aren't necessarily explicitly acting on the water body, but there are many terms in the heat balance that are functions of, say, pressure and relative humidity, and so those get used. So moving into the model theory here, the form of this equation looks fairly similar in a lot of ways to the basic hydrodynamic equation that we saw in the last lecture. So we have our X, Y, and Z component of temperature fluxes. That's mostly controlling the temperature in relation to other model grid cells. Here we have the vertical exchange between the layers of the model, and that's mostly controlled by this AB term here, which is the turbulent eddy viscosity. And it's also a function of the existing stratification in the model. The DI dz term here, this is the essentially the shortwave radiation flux, and so there's a lot more included in this term than it might initially appear, and we have a lot more control over how the term behaves. Similarly here with the DT dz term, there's a lot kind of included in that term that isn't necessarily portrayed in this equation. And then finally the source and sink term. And that would be related to, as I said, any kind of inflows that you have. Generally, when you're doing a temperature simulation, you want to make sure that every boundary condition, especially inflow boundary conditions, have a temperature defined. Otherwise, by default, EFDC is going to set those inflow temperatures to 0. And so, of course, due to the density difference between water that's at 0 degrees Celsius and whatever water's in the model domain already, that water may behave differently than you think that water from that inflow would behave. So lunch is just arriving. Feel free to go over and grab some if you want. I'm going to keep going with this lecture here. So now for the temperature module user interface. So that is access. So the first thing that you would do is to turn on that module. Turning on the module, you would just right-click here on this module section, and then it'll bring up another window with checkboxes. And so you would click the checkbox by temperature. And then when you hit OK and you click out of that dialog, this is what you'll see. So that temperature will be added to the module tree here. And we right mouse click on that, and that's what will bring up the dialogs that we'll see in the next slide. So there are several tabs on the temperature module setup. We have the option of several different sub-modules. Here I've selected the C== equilibrium temperature method. There's several others that you'll see. with this method, we can set the minimum fraction of shortwave radiation that's absorbed in the top layer. Here, that would be 30%. And we can also set the light extinction coefficient. So depending on which sub-module you'll choose for heat exchange, you will see different options here for the light extinction coefficients. For example, the legacy temperature module has a fast and slow attenuation rate. And that can help you kind of customize how shortwave radiation is handled in your model. Here are the initial conditions. So we can set the temperature to either be a constant value across the model domain, or we can set it to spatially vary if we know something about the temperature properties of the lake during the initial, or the water body during the initial conditions. The initial conditions can be set explicitly for each layer, or they can be set based on a vertical profile. So for many water bodies, they might have regular monitoring of the vertical stratification and might be measuring temperature at many points along the entire depth of that water body. And so we can use that to assign the temperature automatically. We also have initial conditions here for the bed temperature and then the bed temperature and thickness. And those can also be set to spatially vary, just depending on what you're doing. Boundary conditions here. So the main boundary condition for temperature in terms of the model domain itself is going to be the atmospheric time series. You can have as many atmospheric time series as you want. The typical approach in EFDC is to use inverse distance weighting. So if we have multiple stations that are measuring atmospheric parameters in our model, we can just assign those to a specific location in space, and then whatever, however close those are to our model domain, those will be mixed or blended based on the inverse distance from those points. So you could have temperature stations that are well outside of your model domain, and you can kind of do a broad interpolation. We also have options to set these as spatially varying in that way. And then the other boundary condition here is going to be the temperature time series. This would be the time series of temperature that's going to be associated with a specific boundary condition, so say an open boundary or a flow boundary. In this example, it's going to be a flow boundary. The ICE module here, in this model that I'm looking at here, the ICE isn't set up yet, but yeah, this is where we would do that. We can set time series for ice and then initial conditions for the ice thickness. And then finally here, bed heat exchange. So you set the heat transfer coefficients for bulk heat and then convective heat transfer coefficients. And then here's what I was describing earlier. So this gives us control over how evaporation and rainfall are going to be handled in the mass balance. And so as I said, with this setting here, ignore evaporation and rainfall from ACER. The heat flux due to evaporation is still going to be included in the energy balance of the model, but it will not be included in the water balance of the model with this setting. So just going into the dye constituent theory here. So we have a couple of different options. We have a tracer option where you can set the tracer to decay or not decay. It can be set to a constant decay rate, or it can be a dependent, a concentration dependent rate of decay. We also have age of water, which is another really nice feature, and that will just that's using the same basic dye theory, except that everything's just kind of increasing. The dye concentration, if you will, is increasing with time in relation to the simulation time. And so that can help you track what the residence times are in different parts of your model domain, which may be really helpful for understanding what boundary conditions are important for, say, flushing water out of your system, or so yeah, again here, the terms in these equations are all pretty familiar by this point. So, we have our source and sink terms. Those are extremely important in the dye module. We have exchange in the vertical, turbulent exchange in the horizontal, and then transport in the X, Y, and Z dimensions. This term here you see this WSC. This would be, we can also set a settling velocity and associate that with a specific dye. And so that's the term that would control that. So we can, as I said, we can apply a first order decay rate, which is a function of the concentration in a given model grid cell, and then a first order decay rate. More commonly, what we do is set a constant decay rate. Here we can, and this is describing how we would set that up as the age of water. So one of the great features that was added in EE10 was that we can now have as many dye classes as we want. And this is really, really useful for tracking different source terms in your model domain. So we can look at what the dye concentration is in a model grid cell, and we can say, okay, about this much water came from this boundary condition, this much came from this boundary condition. And so we can get a really clear picture of how water is mixing at different points in our model domain. So here we just have, we see a model that's set up one dye class right now. And then all of the dye settings will be accessed, so the dye module is turned on in the same way that I described for the temperature module. And then we just right mouse click on the dye here in this module tree. And that's what we'll use to access the settings for the dye module. So here's where we would specify the number of dye classes. We can specify the display units of the dye here. So say our dye is meant to reflect some conservative constituent in terms of micrograms per liter rather than milligrams per liter. We can just change the display unit here. And then when we look at the output in our model plan view, those will have correct the units that we specified. And so here you just see the input fields for the 0th order, so constant decay rate, first order decay rate. We can have a temperature adjustment coefficient and a reference temperature to go with it. And we can apply settling velocity to the dye if we want to. And then we can set the initial conditions. And now we can break for lunch. And after we come back, we will start our hands-on exercise. Does anybody have any questions before we break for lunch? Trying to find my mouse here. Okay.